to a greater thermal energy there. All right, the first law of thermodynamics is where we'll continue here. The total internal energy of an isolated system is constant. And it takes some thinking to figure out what we're going to describe here. So let's look at the diagram. The surroundings are a box around a flask with something in it. The flask got something green going on there. The system, therefore, is that green stuff, the mixture of reactants. The surroundings are the flask, the solvent, the room, and the rest of the universe. So there's a system inside the flask. There's the surroundings outside the flask. And so either one of these two cases will be true. Either energy is going to be flowing out of the system to the surroundings, and it's going to have a negative sign because the energy is leaving the system. You end up with a negative sign for energy. So the final energy is less than you had to begin with. And the opposite is also possible. It depends on the example. And energy can be flowing into the system from the surroundings, and it's going to have a positive sign because you've gained energy. So the final energy is greater than the initial energy. We'll be thinking about how these things are going to compare, but the overall change in energy is the difference in the final and initial states. So we're going to be looking at changes of energy from start to finish in various kinds of examples. So here's the relationship we want to hang on to. Final minus initial gives us the energy change. So in doing this, in this thermochemistry, looking at heat change in chemical reactions, we're looking at different kinds of potential places where reactions will occur, and we use some generic-looking flasks in describing these. So the system is part of the universe that is of interest in the study, and the surroundings is around it, right? So the first one is an open system. You can see that it looks like a flask, and there's heat transfer in and out of the flask because it's not got any reason not to. You know, you set your bottle of beverage out, and eventually it becomes the same temperature as the surroundings. The heat will go into the flask gradually, and the water vapor will escape if the top is open. So the exchange here is of mass and energy because there's nothing to keep it from being contained within the system. The second flask in the center here is a closed flask. It's got a stopper in the top, but heat is still going to exchange back and forth. It's not got any reason to keep the heat in because it's just, in this case, looks like glass. So the exchange here is only the exchange of energy. The last one is a special flask. In case you couldn't tell, it looks to be like it's insulated. And so it's an isolated system. And in this case, nothing exchanges between the system and the surroundings. So depending on the experiment, sometimes we will have a closed system. Sometimes we'll have an actual isolated system where no energy or no mass can be exchanged with the surroundings. Depends. Certain kinds of things, gradually we'll get to that. Examples of things where energies are gained and lost. So here's a reaction of methane with oxygen to make CO2 and water. Well, and it tells us that the other product is 802 kilojoules of energy. It's just a number. Don't panic about memorizing such numbers. And that means the change in energy overall, the energy from the final subtracted from that, the energy of the initial of the reactants. So the final is the products, and the initial is the reactants. The difference in energy becomes 802 minus 802 kilojoules. That means that that energy is released because it's a negative number and it's a product. And that corresponds in this example to 1 mole of methane being reacted with 2 moles of oxygen to make 1 mole of CO2 and 2 moles of water. This is, in fact, a combustion reaction. We've talked about these a little bit here and there, but it should be recognized that combustion is a reaction of hydrocarbons with oxygen to make CO2 and water. And so the energy released here is energy changed, and it's negative because it's leaving the system and going to the surroundings. Well, you're burning something, right? Energy leaves, and the energy change here is released in amounts that we describe in terms of moles of things in a balanced equation. We will come back to this specific discussion a little bit later in the chapter as well. Let's see some other examples. So the first law of thermodynamics tells us energy can be converted from one form to another, but it will not be created or destroyed. So the energy of the system plus the energy of the surroundings together has to be, the changes, sorry, for the system and the surroundings have to be 0. Or another way of thinking about it is to say that the energy of the system is going to be the opposite of the surroundings. So in some cases, you'll be able to determine the change of energy in the surroundings and determine from that the change of energy in the system by changing the sign, opposite signs. One gains, one loses. Okay, so look at that there. It's a picture of a burner, probably a Bunsen burner or something like that. Well, it could be a propane burner. This would be propane. And propane can become combusted, if you will. It's extreme oxidation with oxygen to make CO2 and water. And is a very exothermic chemical reaction, gives off a lot of heat, right? And light, of course. And so the chemical energy that is lost by combustion of the propane is equal to the energy gained by the surroundings. Well, the system versus the surroundings. And so the energy lost by one is going to be a negative sign because it's an exothermic reaction. And the energy gained by the surroundings is going to be a positive sign because it's the surroundings is getting hotter, is gaining energy. Another example then is a process that we describe as exothermic, is anything that gives off heat. It is transferring energy from the system to the surroundings, and heat is a product. Just refresh your thought here. Yes, I said exothermic on the previous one. We're going to continue to define the term. Exothermic means it gives off heat, losing energy. And so giving off heat to the surroundings. The reaction of hydrogen with oxygen is a very exothermic process, gives off lots of heat and light and energy, and it makes water. And that's exactly what happened on the Hindenburg airship in 1937. It was filled with hydrogen gas. It was very buoyant in air, but a spark resulted in a fiery disaster. It was in someplace in New Jersey, as I recall. People died. It was not a very, it was a very noteworthy thing in history, but they've changed the design of airships since, obviously. So releasing energy, that's exothermic. Another example of releasing energy, and this one will make you think, is a gas cooling off to a liquid. So if you go from gas to a liquid, it has to cool, right? Cooling off, you're losing energy, and converting a gas to a liquid is also an exothermic process. Might not seem that way right away, but when you think about it long enough, the molecules have to slow down and they're losing energy to go from gas to a liquid. So sometimes we'll look at chemical changes being endo or exothermic, and sometimes physical changes like state changes between gases and liquid. All right, so if it's not exothermic, and I almost said it, the other choice is endothermic, where a process has to be supplied, energy has to be supplied from the system to the surroundings. Heat has to be a reactant. So there's a suggestion here of a mixture in a test tube that's being heated. It could be something of a mercury to oxide. We add heat to it and you get mercury liquid and oxygen gas. It just happens to be that you have to heat that to make it go. You don't always know how to predict these things, so do not worry about memorizing them. Or for another example, if you take energy, you need to have energy to take water as a solid. Oh yeah, that would be ice and snow, right? And those things are going to require heat energy to become liquid. And this time of year, we're hoping for more energy from the sun to convert all that frozen water outside to liquid, but it takes energy to do that. Not automatic. Another reaction we've talked about and demonstrated on a smaller scale is a thermite reaction, where aluminum reacts with rust, namely iron oxide, and it's a very strongly exothermic reaction, so much so that you get a shower of sparks of molten iron. So the aluminum with the iron 3 oxide, that's what this is here, right? Remember our formulas. The products then will become molten iron and aluminum oxide. And so if you have a sense of humor, you'll tell us that chemistry is minus delta H. Delta H reflects an exothermic reaction. So anything exothermic, we'll talk about delta H as being negative. Gives off energy, it's all exciting, right? All right, now, further topic in this section is a little funky to think about. It's called state functions. And state functions are properties of a system, a reaction or such, that has a value that depends only on the present state or a condition of the system, not on the path used to get there. So it's position, for example. And so the state function is a position. So if you're going from California, where they grow avocados, to Boston, Massachusetts, we don't care how you got there. We don't care how much money it took you. It doesn't matter which path you took. Those are not a state function. But where you are situated, that is a state function. So it depends on where the present state is. You're either in California, you're in Massachusetts, whatever route you took to get there, whether by car, by plane, by bus, who cares? Those are positional things. So in chemistry, we have certain state functions we like to think about too. And we're going to get to these gradually. So thermodynamics means we're going to be studying the state of the system, and we're going to think about macroscopic properties, things that we can see and measure. And they're going to be things like the composition, energy, temperature, pressure, and volume, for example. And so we'll look at different chemical compositions, chemical formulas, and we'll look at these things that have variables that have single convenient letters. So we're going to look at interconversion of heat and other types of energy and think about how some of these are going to be state functions. So energy is one of them. And the stereotypical example is to think about the energy it takes to get from the bottom of the mountain up to the top of the mountain. Well, you got two different hikers here. One took the blue path, one took the red path, and obviously the blue path hiker was going a shorter distance, but man, oh man, they're probably huffing and puffing when they got to the top. But potential energy by position, in other words, of hiker 1, the blue, and hiker 2 is exactly the same. Their potential energy is the same even though they took different paths. So that potential energy is a state function. So the energy at the beginning compared to the end, at the energy at the end, that change in energy is exactly the same for the two, in spite of the fact that the red hiker took a lot more steps to get to the top, most likely. Other things that are going to be state functions are going to be related to pressure and volume and temperature, things that you can measure in reaction systems. And so the changes of pressure and volume and temperature from start to finish are what we're going to be looking at that are state functions, and say how the change in pressure, the change in volume, the change in temperature is simply the difference between the final and the initial in each of these cases. Okay, this will be enough of this conversation for this part of the chapter. I hope it feels a little bit helpful to you. All these topics are a bit awkward to begin with. Good luck on your homework. See you in class.